So, today we will continue our discussion on optical properties, because this course is about optoelectronic materials, and optical properties is a very crucial aspect of making devices. So far we have seen how the basic optical parameters of a material, refractive index and extinction coefficient are based on how light interacts with the matter. Then based on those parameters, we derived what is the absorbance and reflectance of a surfaces, and the fact that it is not just the n and kappa, the surface roughness and so many other parameters, the inhomogeneity of the material itself can give rise to different effects like scattering. So, all these things have to be kept in mind when we are talking about interaction of light with the matter. For example, let me extend my discussion from materials to thin films, because most of the optoelectronic devices we are going to discuss are going to be in the form of thin films. So, in the last lecture I discussed the reflectance property of a surface. So, let me take an example. Let us say if I am working with a solar cell which is on a substrate which is made of glass, and so generally glass is going to be in few hundred of microns, and then the device would be in maybe few microns. This could be an example of a thin film, for example, thin film solar cell, where you are making the solar cell on a glass substrate. And on this optoelectronic devices, the light is shining from the glass side. Now, my purpose here in this device, if I am using it as a solar cell, is to absorb as much light as possible in my active area of the device. Now, if we so far what we have discussed it if I have this glass substrate taking the refractive index of the ambient as 1 and for glass as 1.5. I have developed earlier a formulation for finding out what is the total reflectance, how much light is reflected back, which is given by, in normal incidence, let me say it is going to be given by 1.5 minus 1 over 1.5 plus 1 and square of these. This is what we did in the last lecture. This basically comes from the normal incidence, can be shown to be this for both polarization. If we evaluate this, what we find is that this is almost 0.04, which means at normal incidence 4% of light is reflected back. Now, this may not be so bad if you think it is just 4%, but you know that if I take grazing incidence, Rg is approximately 1, it is very close to 1, which means that most of the light which comes at the grazing angle is reflected back. So, when I am talking about a device like solar cell, and these considerations are important, basically I will be getting light which is not going to be directed only, it is going to be coming from all directions. And as you can see from normal, as you go towards the grazing angle, reflection can be as much as 100% or as low as 4%, which means a lot of light is lost because of this effect. And hence it becomes important to figure out how we are going to change this, and one of the solutions which is used in solar cell and many other devices also is to use anti-reflection coating. So, in order to understand anti-reflection coating, what we need to do is we need to understand how the optical properties, how the material behaves, or what are the optical properties of a material when it is in a thin film form. So, this is what we are going to discuss today. We want to figure out how would be reflectance, transmission, and these are the two things we will discuss, and you can even worry about absorbance in some case will change when your material is in the thin film form. Thin film form means that the material one dimension is very, very small, the other two dimensions might be all right. So, now when we have this situation, how would the material respond to the light? That is what we are going to start looking at today. So, we are interested in finding the behavior of a material which is in a thin film form, and let me draw first a cartoon on what will happen when the material is in thin film form. So, let me take this material which has a refractive index n, and for simplicity let me say that this is a free standing substrate in air. So, the two interfaces are between air and the material and the air itself, and this dimension of the material is thin enough, the d is thin enough to the order of the wavelength of light, then what is going to happen. So, let us first build up what all will take place when this is the case, and then we will discuss the mathematical formulation for it. So, initially what will happen is, if let me think of a light coming at an angle, and as we discussed, let us say at this interface at incidence angle theta. Now, because of this n and 1, some of it will be reflected back, and then we discuss the case that and we know, and we have shown that this angle will be the same as the incident angle, and the angle at which it is refracted is going to be phi, and we know thus from Snell's law that sin theta is equal to n sin phi. Now, this light is transmitted. In the earlier description, we just looked at this problem, the reflection or refraction at one single interface, but when the film is thin enough, this light which is transmitted then comes and sees the second interface. Now, what happens is at this interface also it is going to experience refraction and reflection, which means this angle, which is again going to be same as phi. At this angle, some of the light is going to be reflected back, and the other part is going to be transmitted, and from the angles you can easily show that this angle at which it comes out is again going to be theta. So, basically as the light passes through this slab, the light comes out at a parallel angle to the incidence light, because both the angles remain as phi. So, now this basically your light is still travelling, it is travelling outside, some part of it is transmitted, but rest is reflected back. Again it sees this interface, and it is going to have another event of refraction and reflection at this interface, the angles being same again here, and part of it is going to be reflected back, and it can be shown they will all be parallel to each other. That is the first event, the second interface interaction, the third interface interaction, and then it goes for the fourth interface interaction. Again at this interface it is going to be reflected and reflected back, the light going in this direction. So, you have all these angles as being phi and this angle being theta. So, this is what happens when you have a material in thin film form. You are not only limited to the one single event of refraction and reflection, there can be multiple reflection and refraction event because of this process. So, in the end what you observe far away at this point using a detector is superposition of all these events 1, 3, 5 again. So, all these events is what you would see as total reflectance of this thin film, and once again the superposition of all these transmitted light you are going to see as the total intensity as transmitted. So, this is what we are interested in. When the material is in thin film form, we want to calculate what this reflectance and transmittance is going to be, and it is not only because of one refraction event, but a number of them coming together. Now, in this picture, I would like to make sure that we are clear about the assumptions that we have made here. So, the assumptions in drawing this picture are that I am assuming parallel plate geometry. So, the geometry of the thin film is a plane, parallel plate of refractive index n. And we are going to take up this problem. We at each interface, we are not going to assume any phase change. So, no phase change at interface. And the reason we are saying that is because when we develop this formulation, we are going to use Fresnel coefficient that we derived in the last lecture, where the Fresnel coefficient by themselves will be positive or negative and will give you if there is a phase change at a particular interface. So, we will assume no phase change while developing this formulation, and it will be corrected when we given the equation for the Fresnel coefficient. So, let us first before proceeding further, let us look at when I add up, when I am trying to see the total reflectance because of this thin film and total transmission, I am going to add up the intensities or the electric field vector of all these reflected rays, and I am using a single ray picture. You know, the light is going to be in the form of a beam, but for clarity we follow a single ray here, and then I am going to add up all the electric field vectors for transmitted ones and see what is the total interference I get, and that would be my total R. So, first thing I want to do right now is to calculate what is the phase difference between, for example, let us say the ray 1 and 3. So, the ray 1 which comes and if it is after the first thing, the one amount reflected is 1 R, and then it follows through, has a reflection at interface 2, continues to 3 and gets transmitted at 3. So, this will be 3 R, that is what I need to add up. So, when I am trying to add this up, I need to know the phase difference between 1 and 3. So, the phase difference I am going to calculate by looking at the path difference in these two rays. So, this ray has moved from this point A to B. If I am trying to look at it far away in some time t, in the same time the one which was refracted has gone to 2 and come back to 3. So, basically the path difference here is going to be, let me make some marks here, this is going to be C and this is going to be D. So, the path difference between 1 R and 3 R. So, let me give it the name 1 R and 3 R, the path difference is going to be 2 times, or let me make it first, it is going to be AC plus CD minus AB, right. So, this path that the ray has travelled and this path that the 1 has travelled and this path that 3 has travelled. So, if I am looking at interference in these 2 at time t, I am looking at the interference because of this path difference that is written here. Now, we can simply simplify these equations because we know that what is theta and we know the relationship between phi. So, basically AC is what? It is related to D, right. So, AC plus CD, because this is phi and this is also phi are same. So, I can write it as 2 AC minus AB, because AC is equal to CD. What is 2 AC? 2 AC is nothing but if I take this angle which is phi. So, it will be cos of phi is going to be equal to the d over AC. So, AC is going to be d over cos of phi, right. So, that is going to be AC. What is going to be AB? Now, we can look at AB also. AB is because this is perpendicular, in order to look at the path difference, this is perpendicular onto the ray 1 from this point. So, AB is going to be basically AD, and this angle is going to be 90 minus theta. So, it is going to be cos of 90 minus theta, incidence angle is going to be equal to AB over AD. Okay. So, we know that cos of 90 minus theta is sin theta. So, I can write for AB basically AD sin theta. Now, what is AD? AD is double of this point, it is double of this exactly. So, AD is nothing but d by sin theta 2 times AD is going to be, let me just first write it in the form, AD is going to be 2 times, let me mark this as maybe O at this point. So, AD is going to be 2 times AO, and AO is cos of sin of phi is AO by AC. So, this is going to be AC times sin phi. Okay. So, the way we are proceeding here. So, AB is going to be AD 2 times AD 2 times AD 2 times AC times sin phi. So, it is going to be 2. AC we have already shown is nothing but d by cos of phi, then this multiply by sin of phi, and I am writing about AB. So, this is AD times sin of theta. So, this is what I get as a phase difference. Phase difference between 1 and the 3R is going to be 2d by cos phi minus 2d by cos phi sin phi sin theta. Now, there is something which is very important here. This is actual path difference, but when in last lectures we have shown that the light travels at a slower velocity inside the material. So, when we compare the path difference inside the medium and outside, I have to take the optical path, and optical path is n times the actual path difference. So, for the AC, this is going to be actual path difference time, I should if I am looking at the path difference here, it should be this times n. AB is in air, so that will remain 1. So, it is going to be n here. So, the path difference between 1 and 3 is going to be 2 times d by cos phi n, because we are looking at the travelling of the wave ray inside the medium, and for AB it is not inside the medium, n is 1. So, this remains the same. So, this would be my difference in the 1R and 2R. Now, this can be easily reduced into a more easier solution, and if we do that, we can write this as we will use the Snell's law here, and let me take this to the next point. So, this will become 2d over cos phi times n minus cos of phi. Sin of phi can be taken as sin theta over n. So, it will become sin square theta divided by n. So, the difference, the path difference then comes out to be for any consecutive rays is going to be n times 2 d cos phi. This can be easily seen here, that the path difference that you get between 1 and 3 and the path difference that you get between 2 and 4 is same. So, basically all consecutive rays which are either being reflected or transmitted in this case are all going to have the same path difference, and which will be given by the path difference between two rays that we are adding is going to be either in reflection or in transmission is going to be equal to n times 2 d cos of phi. Okay, so, we know the path difference. Now, we need to add up all the rays in order to calculate the total intensity. So, we need to figure out what would be the intensity of each reflected ray, and so we will be using the Fresnel coefficients that we have developed in the earlier lecture to figure out what is the total intensity that I am going to use, and we will spend some time to develop this formulation in this on this figure, and then it is basically a mathematical addition. So, let me say that let us say the amplitude, the incoming amplitude is A, and then I know from Fresnel coefficient if this surface, if it is getting reflected from this surface, let me call that fraction as small r. If it is getting transmitted in, let me call that as t. So, the light which is then reflected back is going to be its amplitude is going to be A times small r. The amount which is reflected at angle phi is going to be A times t, and then this will be at angle phi. Now, again when it comes to this end, it is going to be reflected, what is reflected back, let me, that is going from n to, this is refractive index n to 1. So, going from n to 1, let me call this n prime, and this was going from 1 to n. So, that was r, and what will be transmitted, we will call that as t prime from this interface. So, what is going to be coming out here is going to be A times t prime, and what is going to be reflected back here is going to be A times t times r prime. Now, this gets reflected to this n, and again it is the same interface going from n to ambient. So, this is going to be r prime coefficient for whatever is reflected, and whatever is transmitted is going to be t prime. So, this then what is going to be collected at reflection is going to be A times t prime r prime, that is the transmitted one. What is reflected here is going to be A times t times r prime square. So, you can follow this again. At this interface, it is going to be reflected and transmitted back again. So, the amount which is transmitted is going to be A t prime r prime square, and the amount which would be reflected is going to be A t r prime cube. Okay. So, this series will continue in that direction. And we have already calculated, when I am going to add up the intensity from ray, let me number them now as 1, 2, 3 on this side, and on the transmission side as A, B and C. So, when I am adding intensity, I will have to take the amplitude that is reflected plus the phase difference with the between 1 and 2 and 2 and 3, and I know all that phase difference is going to be n times 2 d cos phi. So, having done this, now we can write the expression for the total intensity. So, in this expression, since I have taken the magnitude to be A for the incoming incident wave, the incident intensity is A times the conjugate multiplication A star, and ray 1 is going to be A r, ray 2 is going to be A t t prime r, and the exponential I delta, the phase difference. And phase difference we have already calculated between consecutive rays is going to be 2 pi by lambda times the delta that we have calculated for r or for t. Is going to be the same value, which is n 2 d cos phi. So, phase difference is effectively 4 pi n d cos phi over lambda. So, we will keep this picture in mind and develop what would be the total reflected and transmitted ray is going to look like. So, we first write the total amount of the amplitude which is transmitted. So, we are looking at total A t on this end by adding up all these here, and then I will also look at what is the total amount reflected from this thin film later. So, A of t, and following the same picture, is going to be basically A t t prime plus A t t prime r prime square. So, we are going to add up this times the path difference, then times the path difference with respect to this will be twice, then fourth it will be 3 times path difference. So, we will have A t t prime, and this is going to be constant throughout. So, I can take it out of the bracket, and the other terms are going to be 1 plus r prime square exponential I the phase difference. So, this one has a phase difference of I delta. The second one is going to be r prime to the power 4 exponential I 2 delta, and so on so forth is going to go in this direction. The let me write the nth component, that is going to be 2 times n exponential I n delta. So, we are going to add it up, this is going to be a series. So, just writing it in more simplified form, I can write it in a series as A t t prime summation of the series for let me make it m, because n is also refractive index, m going from 0 to m going to maybe large number of rays that we are going to add up. And so, this is going to be n is going to be very large, to n exponential I m delta. So, for the problem where r prime is small, and also that we know that delta is small. Basically, the point we are making here is, although I have drawn it so clearly as if this ray is so much far off from the next and so on, in actuality they are very close. So, basically the path difference between 1 and 2 is very small, they are very close to each other, that is why they are able to interfere and give you an effective reflectance and transmission value. So, delta is also small, we have shown it enlarged in the earlier figure. So, if I do that, this is basically a geometric series. So, I can write A of t as A t t prime divided by 1 minus r prime square exponential I delta, and then this now I know the amplitude. What I am interested in is calculating what fraction of the light is getting transmitted through this thin film of thickness t, that is basically nothing but the complex conjugate multiplication of the overall amplitude, and we can do this easily, and this will become A square t t prime square divided by 1 minus r prime square exponential I delta, and the complex conjugate of it exponential I delta. Now, one can simplify this easily, and this will become what is A square, that is basically the incident light I naught, t t prime we are going to define this as a parameter capital T, which is based on the two interfaces that we have. So, we call it I naught T square, and in this symmetric interface we will see that the relationship which holds true, and r prime square I am going to call that as capital R, and this is then going to be 1 minus 2 r cos delta plus r square. Because of where we have taken a symmetric problem where the film is sandwiched between the two similar ambient surfaces, what we can what we know is from Fresnel coefficient we can easily show that r plus t that we are showing here is equal to 1 for this particular case. So, r plus t is equal to 1. So, we will use that relationship, and if we simplify this further, we can write this as I naught over 1 minus 2 r I naught t square is 1 minus 2 r plus r square, and I want to use the algebraic expression here to write sine square the phase difference divided by 2. Now, this becomes then 1 minus r square and t square, which basically means I can write this as I naught divided by 1 plus 4 r over 1 minus r square sine square path difference. So, this is my total transmitted intensity, which is basically the total intensity by adding all these rays. So, I t is nothing but A t star, and I have shown this comes out to be this value. Similarly, I can do this for A r, and you can do the whole exercise. Let me write just the first term here. So, A r is coming out to be nothing but if I add up all the cases 1, 2, 3 and so on so forth, I will get A r plus A t t prime r prime exponential I delta plus A t t prime r prime cube exponential I 2 delta plus so on so forth, and then I can write this expression as if it is going to be I can write it as A of r I am trying to make it simpler to do the final analysis. So, I can take A t t prime over r prime out. So, there is no r prime, which means I have to multiply the rest with r prime. So, if I do that, if I take A t t prime and multiply the whole thing with r prime, then I am going to get here r square, r prime square 1 plus r prime square exponential I delta. So, if I have done 1 here, I should overall subtract a term A t t prime over r prime. So, that takes care of the 1. This becomes r prime square e to the power I delta plus A t t prime will become r prime to the power 4 2 delta and so on so forth. So, I am doing this some manipulation, so that I can write it in a form which I have already calculated. So, then this becomes A r r prime minus A t t prime, this comes from here, plus this is something which we have already calculated. This is what we had, A of A t transmitted was this term. So, we can write that as it is, and this will be A of t overall r prime. So, this is the total after interference, the amplitude of all the rays which are reflected. Now, as we mentioned earlier, because the way we have taken this problem, the r is equal to negative of r prime, and r square plus T T prime is equal to 1. So, using these conditions I can easily show that A of r is equal to negative of A plus A t, which has been calculated divided by r prime. Now, if I know this, my interest is actually to calculate what is total reflected, which is nothing but A r star, and if I try to calculate that, this will give me A square minus A t plus A t star, the complex conjugate of it, plus A t star, which we have already evaluated, divided by r prime square, which is capital R. Now, one can do a number of simplifications here to bring it in the form where which is similar to what is I t is. So, we are going to use the same relationships that we have used, and use the relationships for I t that have been shown earlier. Basically, I t is equal to this value. So, wherever we need to put in cos delta, we can change it in terms of I t and r. Eventually, we can show that I r comes out to be nothing but I naught divided by 1 plus 1 minus r square divided by 4 r sin square, the phase difference delta by 2. So, we have not done the simplification steps, but you can see that I r will become equal to this. Now, we can notice few things here. If you look at the I t and I r, that is the total light which is transmitted from a film or reflected, you can easily see that I r plus I t is equal to I naught. So, the total there is no amount of light which is lost. The total which is incident is either reflected and transmitted, which is the case because we have assumed a non-absorbing film. The film is not absorbing, and since all the rays are getting interfered, so there must be energy conservation. So, the total intensity which is reflected plus total which is transmitted is equal to the total that is incident, and that is seen in this formulation also. Now, what is the implication of this effect is the total I r from the film. Now, if we look at the total effect of reflectance, it is basically showing, and I am going to make some generalization now. So, I started with a film which had n is equal to 1 on both sides, and the film was inside, but in general when I am dealing with devices, probably one side is the ambient, the other side is the film, and here you will have a substrate or some other film which would have N 2. So, generally you will have this case. I am not going to rederive this case, but if you have this case, you can see that instead of writing r prime, you would be writing it between N 1 and N 2. So, formulation will be developed similarly, only difference is r prime and t primes are going to be different in this particular case. And so, if we you take this case and try to plot for this case, derive I of r term and I of t terms, and plot what will happen to the reflectance as a function of thickness of the film. Okay. So, I will use the same terms, only thing is r prime is going to be different. Now, we will be using N 1 and N 2 for a non-symmetric geometry. So, I am going to plot I r, and I am going to plot the optical path length n times d, the film thickness. The optical path length will be refractive index times d divided by wavelength lambda. So, it is important to realize that all those equations that we have written, the n it is written for a particular wavelength. Since refractive index is a dispersive property, with wavelength it changes. So, I am going to plot this in terms of n d over lambda, and I am interested in one will plot it up to ratio 1 when optical length is equal to the wavelength of light. Then what will happen? So, if I had, for example, just the glass, let us say there was no film and there was only glass, then what would be the reflectance? We calculated in the beginning, this reflectance is going to be equal to 0.04, right. So, this is for N2 equal to 1.5 and D is equal to 0. So, there is no film, I have a 4% reflectance. Now, let me put a film on my glass for N1 and let me change N1, let us say is changing from 2.0 to about 1.2. What will happen to the reflectance? Using these equations that we have developed, and but using the right t and t prime depending on what problem we have developed. If we plot this value, then what we get here is, this goes almost all the way up to 2. For this particular case, I am going to get for 1.2, this is when N1 is equal to 1.2. When N1 is equal to 2, then I am going to get a very high reflectance, almost going to the fraction twice to up to 2. This is for N1, if the film is 2.0. If it is somewhere in between, it is going to be maximizing. Then if it is, let us say something like 1.4, so N1 is equal to 1.4. So, this is not surprising, because we know that this interference effect is going to be oscillating with thickness. So, when you have certain thicknesses where the path differences interfere constructively, you can see that the intensity of the light increases quite a lot, and whenever you have the path differences that would cancel out with each other, if the refractive index is low, you would also get the lowest intensity. So, you can easily see that the maxima and minima in the intensity come at certain values depending on what N1 is. Now, it has very interesting implication, which means that if I have N1 at 1.2 at this value and at this value, my reflected light is 0, right. So, which means that if I take a glass substrate and if I put a material of wavelength 1.2, then this is basically acting as a anti-reflection coating. There will be no reflection from this surface. So, this is how I create my anti-reflection coating, which is basically in going from 1.0 to 1.5, I put in an intermediate refractive index material in between, and if the thicknesses are right, if I have the right thickness, then I will have reflection. The total reflection from this surface is going to be 0, and this is actually used in solar cells in order to reduce the reflection. One does use anti-reflection coating to minimize the reflection from the surfaces. The other thing which is also important to notice is that when n becomes 2, see, we can also increase the total reflectance. So, this can also be used in some cases where you want to increase the total reflectance if the refractive index of this thin layer can be changed, can be increased to more than 1.5. So, this is the importance of the optics in thin film form is by playing with the thickness, the optical thickness of the material and the refractive index of different layers, you can change the overall optical behavior of the device structure, whether how much it is reflecting or how much it is transmitting through the layers. So, this is a way of creating anti-reflection coating. One can see very easily that for all values of N1 D, you can find a maxima if you have this at 2 m plus 1 lambda by 4. So, this is like a quarter wave plate that we have studied earlier, where if you have a quarter wave plate, the path difference will add up to lambda by 2 and it will be cancelling out completely. So, these would be the values for the maxima in this case. Now, having done this, I hope it it tells you that when we are dealing with devices which has large number of layers, for example, a typical device may have contacts, semiconductor, another semiconductor. So, you could have a metal contact, you could have a p type semiconductor, you could have a n type semiconductor, and then you can have maybe a transparent electrode. So, a particular device may have many different kind of layers, and then this becomes even a much more complicated problem, which we are not going to do in this course, but it just to appreciate that whatever we have developed with the first single interface, then we looked at the behavior when we had two interfaces, and we saw some drastic changes and how we can play with the thickness of the film and create very interesting optical effects. But when we have multi layers, these effects will also have to be added up. So, one has to know that behavior of the thin film stack optically, how it is going to be when we are working with the devices in particular case. A very important point that I want to mention here is about the angular behavior. And this is just to highlight that even when we have single interface, you saw that the optical performance of the interface is highly dependent on the angle at which light is coming. Even from daily experience, you may have noticed that your LCD screens or sometimes some displays, you can see it only from a certain angle, and that is because when you have all these multi-layers thin films, they are highly directional. It is only in particular directions they satisfy the rule for maxima or minima, but in other directions they do not, and hence their response is highly direction dependent, and this has been a major issue of development in LCD type of displays. So, one needs to be aware of this effects of the thin film on the optical performance of the materials when dealing with the optoelectronic devices. This course we do not go beyond this point, but we need to keep this in mind. So, to summarize what we have done in optical properties is we have looked at what is the reason for optical properties, just like we have done for electronic structure. We have looked at how light interacts with the material, the basic parameters that decide the reflectance, transmittance, the inhomogeneities, the roughness of the surfaces, all those things which add up to scattering, one has to be aware of when one is talking about optoelectronic devices. And in addition to that, one has to be aware of when we have in thin film forms different layers, what would be the overall effect of these layers on the optical response of the device.